Hey there! In a previous video we talked about how to name ionic binary compounds, and we looked at a bunch of different examples, and I think that helped us come up with some rules which are generally helpful when you're trying to name ionic compounds. And so in this video we're going to do exactly the same thing, but we're going to look at covalent compounds, and you can see some covalent compounds right down here, and we're also going to look at some acids, and acids can be notoriously tricky to name, but I've tried to distill the process down into a few simple rules which hopefully shouldn't be too complicated. But we're just going to get going right away, and we're going to start with this example right here, and I'm just going to name it for you, and then we're going to see if we can use that name to come up with a process, some general rules for naming covalent compounds. So let's get going. So P4O10, I know this is phosphorus, I know this is oxygen, and I'm going to tell you the name of this compound is tetraphosphorus decaoxide. And we can notice a few things. Let's disregard these prefixes for a minute. Let's just look at the names. So in ionic compounds, we always treat the cation, or we always keep the cation as having its elemental name. And I've done the same thing with phosphorus here. So I've treated phosphorus as the cation. It's not actually the cation, of course, because these are covalent compounds, so there aren't any ions involved. But I've treated phosphorus, when I'm naming it, as a cation. I've kept its elemental name. Similarly, I've treated oxygen as the anion. Because I've appended its ending from oxygen to oxide. So that suffix "ide" is generally used to refer to the anion in ionic compounds, and again, these are covalent compounds, so this is quote-unquote the anion. But now we can take a look at these prefixes. So these should be fairly familiar to you. Maybe they're not, maybe they are. But tetra is the Greek and Latin prefix for 4. That makes sense, of course, because there are 4 phosphorus atoms in this compound. Similarly, deca is the prefix denoting 10. And so 4, or tetra, refers to this 4 here, and deca is the 10. So we use these prefixes to explain, or to refer to, the number of atoms of these respective elements in the compound which we're looking at. And so maybe we can use these rules and apply them to this next molecule. So what do we think the name of this molecule is going to be? Well, I can tell you it's dioxygen difluoride. And again, we always treat this first element, this first atom, as the cation. So in this example, oxygen came first, so it retained its elemental name. In this example, it came second, so it became oxide. In O2F2, fluorine is the second element, and so it becomes fluoride. And again, we just use these prefixes here, these dyes, to refer to the fact that there are two atoms of each element in this compound. And maybe if you need a little refreshing on your prefixes, I've listed them all for you here. They're pretty straightforward: mono 1, di 2, tri 3, tetra is 4, penta 5, hexa 6. Some of the trickier ones, I sometimes forget hepta is 7. Just remember, hepta comes after hexa, octa, nona, and deca. But before we move on to acids, I want to look at a few little exceptions to some of the rules we've generated. And we're going to use these 2 examples to illustrate those exceptions. So what might this be called? What might this compound be called? Well, if we use our rules, we know we've got 1 phosphorus and 5 chlorine atoms. Our prefixes for 1 and 5 would be mono and penta. So, theoretically, this should be monophosphorus pentachloride. And this is almost correct. There's one conventional exception which makes this slightly incorrect. Whenever we have one atom in this first slot, so there's no little number here that means there's only one phosphorus atom, only one atom. In this first slot, we actually do not use the mono prefix. We just say phosphorus pentachloride, and when there's no prefix, we assume there's only one molecule of that first atom, or that first element. But this pentachloride bit is perfectly acceptable. Now what about this, N2O4? Well, again, pretty straightforward. My prefix for 2 is di, dinitrogen, dinitrogen. Prefix for 4 is tetra, tetraoxide, tetraoxide. And this is really nitpicky, but it's the way chemists have chosen to do it. Whenever you see two vowels, that's kind of a mouthful. Dinitrogen tetraoxide, it's kind of awkward to say. So actually what we do is we just get rid of that A. We just get rid of that A. So this, the name of this compound, the second part, becomes dinitrogen tetroxide. Tetroxide. So we've removed the A. We've removed the A. And that's probably not going to lose you more of a quarter of a point on a test or quiz, but it is nice to know, and it does roll off the tongue a bit better. So we've just removed the A. And that's generally the case, particularly for oxygen and oxide. We generally remove that A from the prefix to help us say the name with a little more ease. And so that's it for covalent compounds. Let's move on to acids. And if you're not familiar with acids, maybe you're just trying to figure out how to name them before we actually delve into a study of acids at a deeper level, I'll just give you a brief definition here. The simplest definition of an acid is what's called the Arrhenius definition. There are two other definitions, the Bronsted-Lowry and the Lewis definition, but this is by far the simplest. And according to Arrhenius, an acid dissolved in H2O, dissolved in water, increases the concentration of hydrogen ions. So we can just draw a quick sketch. I've got a glass of water. And I drop some acid into it. Maybe it's HCl, maybe it's HCN. That acid is going to produce hydrogen ions. It's going to produce hydrogen ions. So those are hydrogen ions. And those hydrogen ions, according to Arrhenius, are what give acids their characteristic properties, what makes them corrosive, what makes them sour or bitter to the taste, etc., etc. So that's just a brief introduction, but what we're concerned with in this video is naming acids. And let's dive into a few examples. This is probably the most famous acid right here. It's extremely corrosive. This acid is called hydrochloric acid. And let's take a closer look at this. The first thing to say, and the easiest part of the name, is this acid bit. Whenever you're naming an acid, you always include the word acid at the end of the name, which is the easiest way to do it. But now let's look at the actual components of this acid. So to identify an acid is always going to be composed of an anion. So in this case, chlorine is the anion, and a number of hydrogens. There could be one hydrogen, there could be multiple hydrogens depending on the charge of the anion, and so there's always going to be a hydrogen, of course, because if there were no hydrogen, the acid couldn't donate a hydrogen, and then according to Arrhenius, it wouldn't be an acid in the first place. And so let's take a look at this chloric bit. We might refer to this chlorine, this ion, as chloride. That's how we name it when we're talking about ionic compounds. In general, with acids, whenever your anion ends in "ide", you're going to append that ending and you're going to make it "ic". You're going to make it "ic" in the acid. So chloride becomes chloric. And also, whenever this ends in "ide", you're going to add this hydro. Bit. So there are a few things to remember here. First, always acid. Always add acid to the end. If your anion ends in "ide", then you're going to want to change the ending to "ic", so it's no longer chloride, it's chloric, and you're going to want to add a hydro to the beginning. So let's apply these rules to this next compound. You may remember this polyatomic ion as being cyanide. Remember that if there were a cyanide outbreak, it would be on CNN, and so cyanide is CN. We can tell this is an acid because it's got a hydrogen there attached to its anion. And again, cyanide ends in IDE, and so we can apply the same rules. We're going to add a hydro to the beginning, and we're going to append this to IC. So this is hydrocyanic acid. Simple enough. there are a few others, a few exceptions to this rule, or a few different kinds of acids. And you may or may not, I certainly wouldn't at first try, recognize this polyatomic ion as perchlorate. Perchlorate. So that's ClO4 minus. It has a charge of -1. Of course, it's an acid because of the hydrogen, but this anion doesn't end in ide. It doesn't end in ide. So what do we do with it? It ends in ate. So in general, whenever you have an acid, or whenever you have an anion that ends in ate, you're going to do one of the two things which you did for the anions that end in ide. The name of this acid, let's change colors here, is perchloric acid. So what have I done here? Well, the actual ending to the word is the same as if this anion had ended in ide. It's still ic, right? It's still ic. The difference is there's no hydro. This isn't hydroperchloric acid. It's just perchloric acid. And so in general, whenever you have ate at the end of your anion, you're going to add ic to the end, as you would if your anion ended in ide, but you're not going to add hydro to the beginning. And of course, you always end with acid. So what is this? What is this? Well, this is a phosphate anion. And so I'm just going to do exactly the same thing I did with perchloric acid. This is phosphoric acid. So I've just taken the name of the anion, added ic to it, no hydro, and given it acid at the end. But what about something like this? What about something like this? What is this? Well, this isn't chlorate, of course. You remember this is, of course, chlorite. This is chlorite, so we can't do the same thing we would do with chlorate or with perchlorate or with phosphate, etc. There must be a different rule. And so what we do here, the name of this acid is chlorous acid. Chlorous acid. And again, in general, whenever your anion ends in ite, the ending of this first part of the name of the acid is going to end with us. O-U-S. So ite goes with us. O-U-S. Kind of awkward to say, but there you go. O-U-S. And again, there's no hydro. So the hydro is reserved for anions ending in IDE. ITE is us. What is this? Well, here, you may remember this is nitrite. Nitrite. And so what is this going to become? It's going to become nitrous acid. Remember, the ite goes with the us. And so to help you remember a few of these rules, we've got some questions here. Maybe you want to tackle these first three first. Pause the video, and I'll be waiting for you when you finish. Alrighty, welcome back. So this first question here, this is just a simple covalent compound. And what are we going to call this? Well, this is, of course, dinitrogen. And here's a little tricky part, monoxide. So the di refers to the two atoms of nitrogen. There's only one atom of oxygen, and so we're going to use the prefix mono. But mono has an O at the end, and so does oxide. And so it doesn't become mon-oxide or mono-oxide. We just get rid of one of these O's to get monoxide. So in general, whenever you have two vowels, you're going to cut one of the vowels to make it a smoother sounding word. Similarly, this is just sulfur hexafluoride. So remember that whenever we have one atom in this first slot, we don't include the prefix mono. And then hexa refers to the 6 fluoride ions here. Or not, they're not ions in this case, but we're treating them as ions, although this is a covalent compound. And then this is a little tricky. This is an acid, and this is the acetate ion. And so we're going to call this acid acetic acid. So remember that with the ending ate as an acetate, we don't add hydro, and we make the ending of the anion ic. So that's acetic acid. Alright, just a few more for you to do. So pause the video, and I want you to write out the abbreviations for the following. So I've given you the names. I want you to provide the abbreviations. Alrighty, welcome back. This first one is pretty simple. Remember that whenever we have hydro and ic, the ending the ending of our anion is going to be "ide," and so this is the ending, the quote-unquote anion in this case is going to be bromide, or it is an anion in this case, I apologize. This isn't a covalent compound, this is an ionic compound, it's an acid, so the anion is bromide, the cation is hydrogen, and so this is HBr, hydrobromic acid. Next, a covalent compound, nitrogen dioxide. This is quite a common compound. So the lack of a prefix on nitrogen means we only have one atom, so that's just N. Dioxide means we have two oxygens. That one's fairly straightforward. And this is a little tricky. Sulfurous acid. Sulfurous acid. Well, this OUS, remember, indicates that our anion, in this case, ends with "ite." Ends with "ite, and so it's going to be sulfite. What is sulfite? Well, you may remember sulfite is SO3 2 minus, and because it's 2 minus and this is an acid, we're going to have to plop some hydrogens on there, and to do that, because hydrogens generally take charges of +1, we're going to add two hydrogens.